Welcome back after the spring break, everybody. We will start with sampling distribution. Before the spring break, we talked about normal distribution and how to find the probabilities associated with normal distribution. Now we are going to continue with that process. However, we are going to take one step further and find something called sampling distribution. This is a very important concept, sampling distribution. Okay, so make sure that you're okay with it. So what is sampling distribution? To put it simply, sampling distribution is the mean of the sample means. Mean of the sample means. Now this may sound a bit not so clear. Let me go ahead and clarify it for you. And I like to give this very simple example. Let's say in your data set, you have three simple numbers, 1, 2, and 3. That's all you've got in your data set. What is the average of this data set, which is X bar? X bar is the sample mean. So this is your sample. Please pay closer attention to this example. This is extremely simple example, yet very powerful to understand sampling distribution. Okay, sampling distribution is a concept. The first time around you see it, it may not stick to you as easily. However, if you do see a very simple example, okay, where I explain the sampling distribution concept with that simple example, and you understand that, then you can easily extend it to bigger cases and the concept will be clear to you. So this is your sample, 1, 2, 3. That's all you've got. And your mean for that sample is going to be 1 plus 2 plus 3 divided by 3, because you have 3 data points, which is going to be 1 plus 2 plus 3 is 6 divided by 3. That is going to give you 2, because 3 goes into 6 twice. So your X bar is equal to 2. So remember that number. Your sample mean, X bar, sample mean. Remember, X bar is the sample mean. Or sample average. Then mu is the population mean or population average. Remember these two symbols and make sure that you understand the distinction between these two. So the mean of the sample is 2, which is straightforward. Now, from this sample, what I'm going to do, I'm going to go ahead and create subsamples. Create subsamples. Create subsamples of size 2. Okay, so I'm going to create subsamples of size 2 from this. So I could create one group, 1, 2, right? I could create a group 2, 3. Order doesn't matter, so don't worry about it. I could create a group 3 and 1. Is there anything else that I could create from this sample? Is there any other subgroup or subsamples that I could create from this of size 2? The answer is no, that's all. Now, let's call this X1 bar, the average of this 2, which is what? 1 plus 2 divided by 2 is equal to 3 over 2, which is 1.5. So X1 bar is 1.5. Now, similarly, I'm going to find X2 bar the average of the second subsample, which is 2 plus 3 divided by 2, which is 5/2, that is 2.5. So x2 bar is 2.5. The next one is x3 bar, which is going to be 3 plus 1 divided by 2 is equal to 4/2, which is 2, because 2 goes into 4 twice. So your x3 bar is equal to 2. So keep in mind, from this sample, all the subsamples that you can create of size 2 are this one, and this one. That's all you can do. And for each of these subsamples, there is a mean, okay? So for the first one, the mean is x bar. For the second one, for the first one, mean is x1 bar. For the second one, mean is x2 bar. For the third one, mean is x3 bar, okay? So these are all averages, right? Or means. Now, what I'm gonna do, I'm gonna take average of all these three numbers again. So these numbers themselves are averages or means. And I'm going to go ahead and take the average of these averages, okay? So what I'm gonna find, another average of all these numbers, x1 bar plus x2 bar plus x3 bar, all of it divided by 3, which is going to be and what is it? 1.5 plus 2.5 plus 2, all of it divided by 3, which is 1.5 plus 2.5 is 4, 4 plus 2 is 6, over 3, which is 2. Okay? Which is 2. This 2 is called the mean of the sampling distribution. Mean of the sampling distribution. Okay, so these are the samples. Okay, so different subsamples, I should clarify, subsamples of size 2 that you can create from this. And technically I should call this my population, not really sample. So that way this is going to be just mu. Okay, all right. So in that case, what I'm going to do, look at this number. Okay, this number is 2, and coincidentally this number is also 2. All right, is it a coincidence? I'd like to believe so, but it isn't. Okay, it is not a coincidence. As it turns out that population mean mu, okay, which is this, is the same as the mean of the sampling distribution. Now, mean of the sampling distribution is denoted by mu, but with an x bar. Okay, mu with an x bar. So in essence, we are saying that mu sub x bar is the same as mu. So that's what it is. Initially, let me clarify something here. I said this is a sample. Let's consider that's your population. Okay, that's your population. You can of course have, in this simple case, the population of size 3. In reality, that probably won't be the case. In reality, you will have many more. However, here I have given you this very simple example to clarify the concept. So now let me go ahead and go back to the original example again. 1, 2, 3, that's your population. Okay, 1, 2, 3 is your population, and the population mean, which is mu, is 2. All right, so let me clarify this thing. I kind of forgot, sorry, my apology. This is what I meant to say, mu, even though initially in the video I said sample. So let's call it mu. That's the population with 3 items. And from this population, all the possible samples of size 2 that you can pick is this. So, and their averages are this. And the average of all these averages is this, okay? The average of all these averages is denoted by mu sub x bar. So mu is gonna be equal to mu sub x bar. That's what it is. Now I'm going to go ahead and pause here a little bit. This concept is not so straightforward. If you are seeing it for the first time, it takes a little bit of time to sink in. All right. It takes a little bit of time to sink in, and hopefully this example made some sense. I'll give you more example to clarify this concept of sampling distribution. Okay, any question, anybody? No questions, everybody okay? Now let me go ahead and do another example. This one I haven't done it before. The last one I did before. So this time my sample, I mean my population is this. 1, 2, 3, 4. Instead of 3 numbers, my population has 4 numbers or 4 data points, okay? Something I'm collecting from my population where I have 4 items, and from 4 items, I collect these data points 1, 2, 3, and 4. So that's something I did. And my mu population mean for this is going to be 1 plus 2 plus 3 plus 4. So all of it, sorry, divided 10. By 4, that's gonna be 10 over 4, which is 2 goes into this 5, so 2.5, right? So your mu population mean is 2.5. So I'm gonna put this in the box. Now, let's say I create samples of size 3. This time I'm taking 3 items. All the possible samples of size 3. There is a way you can find it, how many of them are gonna be. So these are 4 distinct items or 4 distinct numbers you can think of. From that, you're picking 3 distinct items, okay, or 3 items where order does not matter. So it's gonna be 4C3, which is gonna be 4 factorial divided by 4 minus 3 factorial times 3 factorial, which is 4 factorial divided by 4 minus 3 is 1. 1 factorial is just 1 divided by 3 factorial, which is 4 times 3 factorial divided by 3 factorial. These cancel out, that gives you 4. So there will be 4 items. So let's go ahead and find those. First one is going to be 1, 2, 3. Second one is going to be 2, 3, 4. Third one is going to be 4, 1, 2. And the fourth one is going to be 1, 3, 4. Is there anything else I missed? 1, 2, 4. Do I have 1, 2, 4? I do.
Because it should only be 4, right?
Yeah. So 1, 2, 3, 2, 3, 4, 4, 1, 2, 1, 3, 4. I think that covers everything. Now, for this one, I'm gonna find the average, which is called x1 bar. That is gonna be 1 plus 2 plus 3 divided by 3, which is gonna give you 2. So x1 bar is 2. Okay. x2 bar is going to be 2 plus 3 plus 4, all of it divided by 3 is equal to 3. So x2 bar is going to be 3. Similarly, x3 bar
9
is going to be 1 plus 2 plus
3.
4 divided by 3. So it's going to be 7 over 3. 7 over 3. X3 bar is equal to 7 over 3.
X3, X4,
Bar
7
is going to be 1 plus 3 plus 4 divided by 3. That is going to be 8 over 3. So your x3 bar is equal to 8 over 3. So these are your average of each of these samples, right? So these are all the possible samples that you can get of size 3 from this population. All right. Now, what is the average of these averages? So this x1, x2, x3, they have a distribution, okay? They have a shape. You don't probably see it so much because your sample size is, I mean, your population is extremely small. But if your population gets bigger, then you will see all these x1, x2, x3, there will be many of them. If you graph them, it will have a shape, all right? So now, what it is, we are going to go ahead and find the average of these averages, okay? Mean or average, mean of these means.
Are you going to change to fractions?
So let's go ahead and do it and see what we get. 2 plus 3 plus 7 over 3 plus 8 over 3, all of it divided by what, 4, right? And 2 plus 3 is 5 plus, look, 7 plus 8. So 7 over 3 plus 8 over 3 is equal to 15 over 3, which is just 5, right? Because 3 goes into 15 5 times. So it's going to be 5 over 4, which is 10 over 4, that is 2.5. Do you see? The mean of this means, which we call mu sub x bar, is 2.5. Look at this number and look at that number. Let me use red so that you can see it. Look at this number and look at that number. This was the population mean, right? Mean. And this is the mean of the sampling distribution. With sample size 3. Mean of the sampling distribution with sample size 3. Okay. Now these two things are the same. So sampling distribution is the distribution of the sample means. So if you look at this mean, this mean, this mean, and this mean, these 4 means, if you graph them, the shape or the distribution of these means is called the sampling distribution. Sampling distribution. If it is not clicking to you, please do not give up or do not get frustrated, because it does take a little bit of time to get a feel for it. It's not easy concept, but in my opinion, this is one of the harder concepts of the class. After that, everything is easy. All right. So sampling distribution is the distribution of the sample means. Okay. So if you have a big population, okay, a population of students at Hartnell College, if you take a sample of size 100, how many samples of size 100 will you get? Many of them. Okay. For practical purposes, this number is infinity. Okay. We have about 15,000 students, right? From 15,000, we take 100 students, right? From 15,000, we take groups of 100. If you do this calculation, this number is extremely large, okay? For practical purposes, this is infinity, all right, for us. Even though it's not infinity, of course, right? It's so large that really crazy large. And of all the samples of size 100 that you could pick from 15,000, for each of these samples, you're going to have an average like this. And if you take those averages and graph them, that is going to be the distribution or shape of the samples, and it is called sampling distribution. And this is an important concept that you need to be comfortable with. Now, just to give you an idea, look at this. This is crazy. Having a population of size 100 is nothing. It's really small. All right. Even our Hartnell College students, the population size is 15,000, and I'm talking about 100. Let's say if Hartnell College had only 100 students, and from those 100 students, I selected groups of 30. That means every time I'll select a different group of 30 students from this group of 100. All right. Hartnell College has 100 students, hypothetically speaking, and from those 100 students, I'm selecting 30, and all the possible groups, all the different possible groups that I could select from this group of 100 is, by the way, this number. And you can imagine how big this number is. This is crazy brain. Okay? I don't even know how many digits are there. Let me see, 4, 8, 12, 16, 20, 24, 25 numbers, I think. Okay, 25 digits. You can imagine how big this number is. This is just for a sample of size 100, this is going to infinity almost for practical purposes. And imagine taking it, if you have 15,000 students, okay, how many different groups of students you can pick of size 300. That'll be like crazy big number. All right. So that's what it is. Now, this just gives you a sense of how big the sampling distribution could be, how big the size. So now this is just one sample of size 30. You could pick samples of size 31. You could pick samples of size 10. You could pick samples of size 99 or even 100. You couldn't pick more than 100 because 100 is the total number of students that you have in this hypothetical Hartnell College. Or you could pick anything between 1 and 100 sample size. Now, sampling distribution is the distribution of the sample averages for particular sample size. Sampling distribution is the distribution of sample averages of particular sample size. So for instance, For this one, I took a sample of size 30, right? How many such samples am I gonna have? This many. For each of these different samples, they're different, they're not the same. Each of these samples are different. And for each of these samples, I'm gonna get an average. Like I got X1, X2, okay? And then that, in my case, is gonna be X29372 760. Do you see that? That's going to be the last one. So if you take all of these things and graph them, that is the distribution, what we call sampling distribution. Now, the beautiful thing about this thing is this. The sampling distribution is pretty much, for our purposes, always going to be bell-shaped or normal. Sampling distribution is always the bell-shaped or normal if your sample size n is greater than or equal to 30. If your sample size n, here, what is the sample size? 30. If your sample size n is greater than or equal to 30, your sampling distribution is always going to be bell-shaped or normal or Gaussian. Bell-shaped, normal, or Gaussian. If your sample size is greater than or equal to 30, your sampling distribution is always going to be bell-shaped. Remember, sampling distribution is the distribution or structure or shape of all the sample averages of sample size under consideration. So in this case, we could have a sampling distribution for sample of size 30. We could have another one for a sample of size 31, another one for sample of size 32. These are different because their sizes are different. Or we could have one for 29, we could have one for 28, and keep going in that direction up to the population size, which is 100, and down at the bottom with sample size of 1. And that is an important concept, sampling distribution. Now, interesting thing about this, so let's say, let's consider these two scenarios. So for n is equal to 30, so for our simple case of this, n is equal to 30, we have the bell-shaped, right? Let's say I make n is equal to 50. That is also going to be bell-shaped, but the difference between this bell-shape and this new bell-shape that's going to be drawn very shortly is this. The one has a less standard deviation, so this is going to be more like this. See, this is for sample size 50, this is for sample size 30. This one is more compact, more narrow, whereas this one is more spread out. So this one has less variation. This one has relatively more variation. Okay, which is to say that this one has a higher standard deviation compared to the other one, higher standard deviation, lower standard deviation. Okay, if your sample size goes up, the shape in and of itself does not change. If your sample size goes up, the shape in and of itself does not change. What changes is the standard deviation. This is bell-shaped, so is this one. What's the difference? This one, in this one, the data is more closer to the center, right? Data is more closer to the center, whereas in this one, data is further away from the center compared to this one. So on the other hand, if I were to, let's say, pick a sample of size 10, in that case, how is it going to look like? So this one has a sample size of 10. So this has even higher standard deviation compared to this one or this one. This one has lower standard deviation. This one has medium standard deviation. This one has higher standard deviation. It depends on the sample size. The bigger the sample size is, the closer the data points are, less the variation is. So let's say if I were to pick sample size n is equal to 75, in that case, it's probably going to be more like that, even more narrower. Okay. The bigger the sample size is, the narrower the bell shape becomes. The smaller the sample size is, the wider the bell shape becomes. That's what the rule is, or that's how it works out. And this is something important. Now, for simplicity, I'm just gonna say that I have a population that is bell-shaped, and from that population, I pick a sample of size 30, and I get another bell-shaped curve. Okay, both are bell-shaped. Now, this is the population distribution. This is the sampling distribution. Look, here the sampling distribution has sample size 30. In the population distribution, always sample size is 1. In the population, it is 1 sample size, because in the population, the items exist as individuals, right? In the population, items exist as individual items. So this is your population distribution. Now, the mean of this population will be right here in the middle. We call it mu. Mean of this is sampling distribution, which is going to be right here, which we do not call mu, but we call it mu sub x bar with a little subscript at the bottom, to the lower bottom of, lower right side of mu, okay? Mu sub x bar. Now, our central limit theorem tells you, so this is the most important thing. Central limit theorem. Central limit theorem tells you that between these two distributions, there is some relationship, which is mu is the same as mu sub x bar. Mu, this mu mean is the same as this mean. It doesn't matter which distribution are you in. Are you in the sampling distribution or are you in the population distribution? It really does not matter. Mu is the same as mu sub x bar. Okay. Now, remember here, what we have done, we have assumed that the initial population is bell-shaped. Okay. I'll make some clarification there. So that's one. Let's say standard deviation for this guy is sigma. Population standard deviation is sigma. Now, the central limit theorem also tells us another very interesting relationship between the standard deviation of the population and the standard deviation of the sampling distribution. And obviously, you may already have guessed, standard deviation of the sampling distribution is written as sigma sub x bar, like mean of the sampling distribution is written as mu sub x bar. Standard deviation of the sampling distribution is written as sigma sub x bar, okay? sigma sub x bar. And the relation between the two is this. There is a relation between this guy, and that relation is sigma sub x bar is equal to sigma divided by square root of the sample size. In our case, we use sample size of 30, so it will be technically square root of 30. In general, we denote the sample size by n, and that's why I have put n here. These are the two conclusions of the central limit theorem. And these are fundamental to the study of statistics. Okay? This is fundamental to the study of statistics. Remember these two conclusions pretty much not only for the rest of this semester, but also for the rest of your life. Okay? So mean of the population is the same as the mean of the sampling distribution. Standard deviation of the population is related to the standard deviation of the sampling distribution through this formula. And that is something very important for you to know. Now, having said that, here is another interesting part. My initial population was bell-shaped, okay? The population that I dealt with was bell-shaped. If it is the case, I can do this. But what if my initial population is not bell-shaped? It's some weird shape. I don't know, I've made it up. This is some weird shape, my initial population. I'm just gonna make it some crazy shape, okay? This is my initial population shape. In that case, what happens? It's not bell-shaped, okay? It's not bell-shaped like this one, rather the blue one, some crazy shape. In that case, how is mu related to mu sub x bar? How is sigma related to sigma sub x bar? As it turns out that this central limit theorem still holds true, except we have to make one assumption. Your sample size n must be greater than or equal to 30. Your sample size must be greater than or equal to 30. If that is the case, in that case, these two conditions are still gonna hold true, even though the initial population has a shape that is unknown. That means it's not normal for sure, okay? If the initial distribution has a shape that is not bell-shaped or not normal, in that case, we need to make sure that our sample size is greater than or equal to 30, okay? If your sample size is not greater than or equal to 30, then these two conditions are not gonna hold true for some arbitrary distribution. From some arbitrary distribution, these two conditions are not going to hold true. And this is the important part. On the other hand, look, if your initial population's distribution is bell-shaped, this restriction doesn't hold true. That means you don't have to have sample size 30 or more. It could be sample size less than 32. It could be n is equal to 29, 28, 27, all the way down to 1, right? If it is 1, then it's the population distribution. That is true only if your population is bell-shaped. Then we don't have this restriction. And these are the conclusions of central limit theorem. And this is a very important concept. You may have to revisit this thing multiple times before you get a true feeling for it, and do few examples, which we will be doing, and make sure that you really get a good understanding of it. It is an important concept. It is so important that we call it central to the study of statistics, or central limit theorem for statistics. All right, any question before I move on, everybody?
No.
So the two conclusions, mu is the same as mu sub x bar, or mu sub x bar is the same as mu. That means population mean is the same as the sampling distribution mean. And sampling distribution standard deviation is the same as the population standard deviation divided by the square root of the sample size. Population distribution, population standard deviation divided by the square root of the sample size. And this holds true only if n is greater than or equal to 30 for any arbitrary distribution, but n could be less than 30 if your population, initial population, is bell-shaped. Okay, so let's move on. We have talked about this. Central limit theorem, we already talked about it. Something here I kind of wanna mention. Z is equal to x minus mu divided by sigma. We had that formula, Z scores formula. There is an equivalent formula for central limit theorem or sampling distribution rather. Instead of Z, we call it Z sub x bar, okay? X, instead of x, we call it x bar, minus, instead of mu, we call it mu sub x bar. But mu sub x bar is the same as mu according to central limit theorem, so we could just put mu instead of mu sub x bar. Divided by sigma, but that should be sigma sub x bar. Then again, according to central limit theorem, sigma sub x bar is equal to sigma divided by the square root of the sample size. So we are going to replace this sigma sub x bar by sigma divided by square root of the sample size. So this is the modified version of the z-scores formula, modified version of the z-scores formula for central limit theorem or sampling distribution rather. Modified version of the z-scores formula for sampling distribution. Now we can do these problems. Okay, I will walk you through these problems. I have done them here, but you have to follow along. Okay, make sure that you follow these problems. And there is a, as I walk through the problem, and you need to make sure that you follow it, the difference in asking the question. Okay, the difference in asking the question. So take a second and read the problem. Okay, Mr. Zuckerberg, the founder of Facebook, recently announced that recent is more than 10 years old, by the way. I made this problem many years ago. recently announced that an average person spends about 50 minutes per day on Facebook, okay, Instagram and Messenger. Basically, his claim was that an average person spends about 50 minutes on the social media. Assume that the time spent on these social networks are normally distributed with a standard deviation of 30. So we are kind of making some assumptions here. The average person spends 50 minutes, so mu is 50. And the standard deviation is 30 minutes. So sigma is 30. And it also tells you that time spent on these social networks or social media is normally distributed, meaning it's bell-shaped or Gaussian distribution or normal distribution. It is bell-shaped and it has a mean of 50 and standard deviation of 30. So if you were to graph it, it would look like this. This mu is equal to 50 and sigma is equal to 30. The sigma part I made up, by the way, okay? Just to create the problem. I haven't done the calculation to find out. I didn't go out and took a large sample and found the standard deviation for that data set to kind of approximate the population standard deviation. Okay. Now, let's go ahead and answer these problems. What is the average number of minutes that a person spends on these social media channels? Note that the sample size is 1. So what is the average number of minutes? That means they're asking you what is mu, which is 50. I should have written here mu is equal to 50. That way, this mu sticks to your head. People really get confused even at the end of the semester, the difference between X bar and mu. X bar is the sample average, and mu is the population average. X bar is the sample average and mu is the population average. Okay, what is the standard deviation for the distribution with sample size 1? So I'm specifically telling you sample size 1. When we are talking about sample size of 1, we are talking about the population itself, not really sampling distribution. If we are talking about sample size 1, we are talking about the distribution of the population. All right. So standard deviation is 30. Okay. Standard deviation is 30, which is to say sigma is equal to 30. Now this time you are not dealing with sample size of 1, you are dealing with sample size of 25. Now if you take a sample of 25 people who use the social media, then what is the average of the sampling distribution? Look, sampling distribution. All right. Sampling distribution. So very important. So this time sample size is 25. So what is the average of the sampling distribution? Now, remember the central limit theorem tells you that mu sub x bar. So now you cannot say this is mu. Like I said, this is equal to mu. This is equal to sigma. You cannot say it's mu anymore. It is mu sub x bar. Okay, because you're dealing with a sample of size greater than 1. N is greater than 1, meaning you're dealing with sampling distribution. N is greater than 1, meaning you're dealing with sampling distribution. In our case, N is 25. So can I use mu sub x bar is equal to mu? That is one of the conclusions of the central limit theorem. We call it CLT. That is one of the conclusions of the central limit theorem. Now, my question to you, can I say mu sub x bar is equal to mu?
No,
No. Why?
because it's not greater or equal to 30.
Who is talking?
Meijin.
Mijin says n has to be greater than or equal to 30, or the sample size has to be greater than or equal to 30 for this condition and the other condition to hold true, right? Here the sample size is not greater than 30. Good. A good observation, Mijin or Mijin. How do you pronounce your name? Mijin or Mijin?
Meijin.
Mijin, okay. Now, anybody else wants to add to the comment that Mijin has? Any other comments, anybody? No comments? That's a good point Mijin made. I want you to participate and tell me. No other comments? Everybody okay? Okay. So, Mijin, thank you for the comment. That's a great comment. However, we don't have to worry about this sample size being greater than or equal to 30 in this case. Why? The reason is that, look, it says it's normally distributed. Population is normally distributed. If your original population is normally distributed, then this sample size restriction does not apply. It only applies if your original population is not normally distributed. In this case, I specifically tell you that the original population is normally distributed. In that case, okay, you don't have to worry about the sample size. So mu sub x bar is actually going to be mu, which is to say mu sub x bar is equal to mu is equal to 50. That is, the population mean is the same as the sampling distribution mean with sample size n is equal to 25. Population mean is the same as the mean of the sampling distribution with sample size of 25. Even though 25 is less than 30, it really doesn't matter because normally distributed. Now, what if I said, so Mijin, I have this question for you now. What if I did not say that? In that case, what would happen? What would be your response? Let's say, hypothetically speaking, I did not put this as part of the problem. I do not tell you that the population has normal distribution. In that case, what will be your response to this question?
Then the answer would be no. Or
Yeah,
that-
we don't know because the sample size n is equal to 25, which is less than 30. So we cannot apply central limit theorem to find the to make the conclusion that mu sub x bar is equal to mu. Therefore, nothing can be said. That's exactly what the answer should be. Because we do not know whether the original population is bell-shaped. Therefore, we cannot apply the central limit theorem unless the sample size is 30 or more. In our case, sample size is 25, which is less than 30. Therefore, we may not be able to apply the central limit theorem. Therefore, we cannot say anything about the mean of the sampling distribution with sample size 25. So that should be your answer for that. Now, okay, what is the standard deviation of the sampling distribution with sample size 25? It's easy. It's going to be sigma sub x bar is equal to sigma divided by the square root of the sample size. Sigma of the original population is given, which is 30, divided by the square root of the sample size, which is 25. 30 over square root of 25 is 5. 5 goes into 36 times. So standard deviation of the sampling distribution, which is sigma sub x bar, is equal to 6. Do you see? Variation, standard deviation in this case is smaller compared to the population standard deviation. So if the population looks like this, the sampling distribution is going to probably look like this. Less standard deviation, less variation, okay, or variance. Remember, variance is the square of standard deviation. So sigma square is variance. So sometimes I will say standard deviation, sometimes I will say variance or variation. So don't get confused by that. It is kind of referring to the same thing. So that's that one. Number 4, this problem has several parts. Now we are getting into more interesting stuff. Find the probability that a randomly selected person spends more than 120 minutes on social media. Find the probability that a randomly selected person spends more than 120 minutes on the social media, which is easy. We know it's bell-shaped, right? With a mean of 50, standard deviation of 30, right? So 120 is going to be right here. So you want the probability greater than 120. So we are looking for probability of x greater than or equal to 120 minutes. Now, from your experience with dealing with bell-shaped curve, you know that you have to convert everything to standard normal distribution. So now let's see. Leonardo Lomeli, what makes a normal distribution a standard normal distribution? What characteristics does a standard normal distribution has that differentiates itself from the other normal distributions? Leonardo, what are those? So I'm asking, what makes a normal distribution a standard normal distribution? Jonathan Martinez, what makes a normal distribution a standard normal distribution? Maribel Mendoza Ortiz, what makes a normal distribution a standard normal distribution? See, I told you guys, these are basic stuff. If you don't know that, you won't be able to solve the problems. And I went over this so many times, over 3 different lectures, actually more than 3, 4 or 5 different lectures. Last 3 lectures, I dealt with standard normal distribution in pretty much every single problem, because we needed to, or we were finding out the probabilities associated with bell-shaped curve or normal or Gaussian distribution. Anybody, what makes a normal distribution a standard normal distribution?
Doesn't it have to do with the mean being 0 with the standard deviation of 1?
Thank you, Araceli. Mean 0 and a standard deviation of 1. How do we go in between these two? Z is equal to x minus mu over sigma. Easy. So corresponding to x is equal to 120, there will be some value of z, which is going to be just 2, by the way, because 120 minus 50 divided by 30 is 2. So finding the probability that x is greater than 120 is the same as finding the probability that z is greater than or equal to 2. Now you can look it up in the standard normal distribution table for z is equal to 2, but that's not the value you are looking for. Standard normal distribution table, it gives you area to the left, but we need the area to the right. So we just need to subtract the area to the left, which is 1 minus the probability of z is less than or equal to 2. Now, if you look up for z is equal to 2 on the standard normal distribution table, you will get 0.9772. That means this area to the left is 0.9772. Now the area to the right is going to be 1 minus 0.9772, which is 0.0228. So the probability that a randomly selected person spends more than 120 minutes on the social media is 0.0228 or 2.28% chance. There is a 2.28% chance that a randomly selected person from the society would spend more than 120 minutes in the social network per day. So I'm gonna take this problem. So actually, let me just bring it back. Any question, anybody, before I move on to the next part of this problem? Because this is a problem where I walk you through step by step from regular normal distribution to sampling distribution. Okay, any question, anybody? This is something we covered in the last 3 lectures. I went over this type of problems in many, many different ways over the last 3 lectures before the spring break. Hopefully you haven't forgotten things during the spring break. If you did, it probably will not be a bad idea to go over all of these things again. Take your time and go over the class notes, watch the videos, which I send it to you every time, and make sure that you are solid on these concepts. Next problem is this. So I put it side by side so that you can see it. Now look, in the last problem, look, a randomly selected person, okay? A randomly selected person right there. In this problem, however, we talk about 25 people. It's not one person anymore. The last one, we talked about the population distribution. Here we are talking about sampling distribution. When your sample size is greater than 1, you're dealing with sampling distribution. When your sample size is greater than 1, you're dealing with sampling distribution. Now we are asking the similar type of question. What is the probability that a person spends more than, not a person, I will clarify it. What is the probability that the average of 25 people, so now this time you don't pick one person off the street and find out what is the probability that he or she is going to spend more than 120 minutes on the social media. But this time you pick, instead of one, you pick 25 people, okay? You pick 25 people and find their averages. You pick 25 people and find their averages. What is the probability? What is the probability that their average is going to be more than 120 minutes? Okay? Because for one person, 120 minutes makes sense, just one person. But for 25 people, you cannot say that just 25 people does more than 120 minutes. It is the average of those 25 people, okay? The average of those 25 people is more than 120 minutes. Now, this time, last time we found this should be lowercase x. We found probability of x greater than 120. That's what we found, which is 2.28%. This time, by the way, we are not asking that. We are going to be asking, find the probability of x bar, not x anymore. Why is it x bar? Because I'm dealing with a sample of size 25, not sample of size 1. So what is the probability that the average of 25 people is more than 120? That is the question we're asking. So this is very important for you to be able to distinguish between these two things. One is for an individual, the other one is for average of group of people. In that case, in this case, that group contains 25 people. The average of 25 people. Okay. All right. So now things change a little bit. So let me go ahead and bring this screen. Now, this time you're dealing with sampling distribution. This is not the population distribution. This is sampling distribution with sample size 25. And this is your mu sub x bar, it's not mu. And this is your sigma sub x bar, this is not just sigma. So mu sub x bar is the same as mu, which is going to be just 50. Sigma sub x bar is going to be sigma divided by square root of the sample size, which is going to be 30 over square root of 25, which is going to give you 6. We found it before. Now, look, we still need to convert this into standard normal distribution, which is a mu sub mean of 0 and sigma of 1. How do you go back and forth between these two? Again, we use the z sub x bar formula. Z sub x bar is equal to x bar minus mu sub x bar divided by sigma sub x bar. X bar minus mu. I replace this mu sub x bar by mu because the central limit theorem tells you mu sub x bar is equal to mu. Why can I use the central limit theorem even though my sample size is less than 30? Because initial problem tells you that the population is normally distributed. That's why even though the sample size is less than 30, we can still use the central limit theorem. So that's why I can say it's mu. And standard deviation is, instead of sigma, I put sigma over square root of n. So I just do the math. X bar is the point of interest, which is 120, which is X bar. So I'm going to be looking for this tiny little region, and there will be corresponding Z value, and I'm going to be looking for this. So finding, oops, what has happened? Finding the probability of X bar. So let's see the different color. X bar, this should be lowercase. Finding X bar greater than 120 is the same as finding Z sub X bar greater than 10, because we found Z sub X bar to be 10. Finding the X bar, or the average of 25 people being greater than 25, is the same as probability that Z sub X bar, we use Z sub X bar, it should be here, Z sub X bar, okay? We use Z sub X bar just to identify that we are dealing with sampling distribution. We are not dealing with the population in and of itself. Just to identify that, we put Z sub X bar is greater than 10, which is the same as 1 minus the probability of Z sub X bar less than 10. This is greater than. Standard normal distribution table does not give you greater than value. It gives you the less than. It gives you area to the left. It is cumulative from the left. Standard normal distribution table is cumulative from the left, meaning it gives you the probability of being less than or equal to. Probability of being less than or equal to. So this is probability of Z less than or equal to 10. Now, if you look it up in the table, Z score of 10 doesn't exist. It's so out there. The table actually goes to 3.5, I think. So at 3.5, you get 0.999, bunch of 4 nines or something, 5 nines. I forgot. Now, since the table doesn't go beyond this, we'll just take whatever the highest value we can get from the table, which is 0.9999. There should be a couple more nines at least there, maybe another 3-4 more nines. So, which is, by the way, 0.0001%. Okay, 0.0001%. So the chances that if you randomly select 25 people, the average time that all of them together spend on the social media is more than 120. That is extremely small, very small. This number is actually not the true number. The true number would be even much lower than this. True number will be much lower than this. So that is very important. See, what the moral of the story here is this. If I ask you the following thing, hey, I randomly select one student from the class, what is the GPA of that person gonna be? It could be any number, really, right? Yeah. If the person has happens to be a good student, might have 3.9. If the person happens to be a bad, not so good student, would be could be 2.5 or 2 something, or even less than 2. What it says that individual GPA can fluctuate a lot. Individual GPA can fluctuate a lot. However, the average of 25 students GPA is not going to fluctuate a lot. That means it will have less variance or less standard deviation. Remember, in the last part, in part 5 of this problem, the standard deviation was 30. Now, for this problem, the standard deviation came down to 6. Why? Because we are dealing with a sampling distribution with sample size 25. So we have to divide the population standard deviation by this. Okay, that's how you do it. Is this okay, everybody? Any question, anybody, before I move on?
Actually, I just realized something.
Yeah.
So you know how you have 120 minus 50, but you have 60? Wouldn't it be 70? So doesn't it change the whole answer?
Yeah, there is a typo with this problem. I forgot to correct it. Thank you, Araceli.
Okay.
120 minus 50, that's actually 70. So this standard deviation would be probably 11.66. Okay. So this is gonna be, thank you for catching that, 11.66, but the table even doesn't go to 10, let alone 11.66. So let me just clarify it since she mentioned it. So it's gonna be probability, so the number was z sub x bar was 120 minus 50 divided by 6, which is 70. And I think I made the same mistake over there too in the last problem. Let me just bring that one up. See, there's a typo here. So this should change answer a little bit. This 120 minus 50 is not 60, 70. So this should have been 2 point something. Okay. So there is a typo here, 2.33 or something. So please go ahead and correct it. I keep forgetting to fix this typo. But anyway, so this is going to be 70 over 6, which is going to be 11.66. So 66. So technically probability of x bar greater than 120 is the same as the probability of z sub x bar greater than 11.66 instead of 10. This was 10 before, but it really doesn't make a difference because this is such a high standard deviation that it's not even in the table, it's off the chart. Okay, any question, anybody else? No questions? Okay, so this should be 11.66. Okay, this is 70. Now, in the next problem, I ask you, find the probability that a randomly selected person spends between 40 and 60 minutes. You will need to find the probability that a randomly selected person spends between 40 and 60 minutes, which is pretty easy. We did that before, so I'm not going to. So remember, randomly selected person, just one person, your sample size n is equal to 1, meaning that you're dealing with the population. In the next problem, you can guess n is going to become 25. Then you're dealing with the sampling distribution. Here you're dealing with the population distribution. Here you're dealing with the sampling distribution. Okay. Now, this is easy. Probability that someone spends between 40 and 60. So you just need to convert these 40 and 60 to z-scores, which is going to give you 40 minus 50 divided by 30, right? Which is going to be negative 10 over 30, which is approximately negative 0.33. And similarly for 60, you are going to get z positive 0.33. So this in essence comes down to, so I did it here. So probability of 40 less than x less than 60 I could add one line here. Is this same as probability of negative 0.33 is less than z is less than 0.33. Excuse me 1 second. Now, which is the same as saying probability of z less than 0.33 minus the probability of z less than negative 0.33. If you look it up in the table, you should get these values, and at the end, it should be 0.2586. So there is a 25.86% chance that a randomly selected person, 25.86% chance that a randomly selected person will spend between 40 and 60 minutes. Now, as I said, this time I'm doing it for 25 people. Okay, for 25 people, what is it going to be? So for 25 people, we are in the sampling distribution realm. So we need to make sure that we do it differently. For 25 people, we are talking about sampling distribution. So average of 25 people. So that's why it's X bar. What is the probability that the average of 25 people fall between 40 and 60? So it should be X bar less than 60 minus X bar less than 40. Or equivalently, I could say your Z is gonna be between negative 1.67 and positive 1.67. So I could say probability of 40 less than X bar is less than 60 is the same as probability of Z between negative 1.67, I mean not Z anymore, Z sub X bar between 1.67, which is the same as probability of Z sub X bar being less than 1.67 minus the probability of Z sub X bar being less than negative 1.67, which is gonna give you, which I write down here, 0.9525 minus 0.0475 is equal to 0.905 or 90.5%. There is 90.5% chance that average of 25 people is gonna fall between what? 40 and 60 minutes compared to a single person. So here, let me use red so that you can see it. For a single person, it's 25.86% chance that he or she will spend between 40 and 60 minutes, whereas for a group of 25 people, the average time spent for those 25 people, the chances that it will fall between 40 and 60 is much higher. That means it does not fluctuate as much. Remember how I gave you the example of one student's GPA that could jump around all over, right? Whereas the average of 25 students' GPA is not going to jump as much. So it's going to have less variance. Okay, it's going to have less variance. So it is important for you to understand that thing. Important for you to realize that standard deviation would be higher for one person, whereas standard deviation is going to be lower for multiple people. And that's exactly what you see. Where does it come from? It comes from actually this. See, this thing, sigma over square root of n. That's what makes the z score much bigger, the square root of n. So if you simplify it, x bar minus mu divided by sigma over square root of n, which is, by the way, the same as x bar minus mu times square root of n divided by sigma. If you recall correctly, in our last formula, it was x minus mu divided by sigma. Now we replace x by x bar, the symbol, and all we do is multiply the result by the square root of n, okay? Multiply the z value for the regular case, for the population z value, okay? For the population, when we are converting it to z value, we multiply it by we take that z value and multiply it by the square root of n, and that is why you see your z here is 1.67 negative, whereas over here is 0.33. See, 0.33 times 6. That's what we. It's not 6, 5. Okay, we multiply it by 5. Why? Because square root of 25 is 5. So if you multiply 5, so 1.65. So this is what it comes, roughly close to this. Or this rather, because positive and negative. So it takes a little bit of massaging the problems, massaging the concepts before it sticks to you in your head. You need to make sure that you see these concepts many times. If you don't understand it the first time around, that's okay. You need to practice and play around with these ideas a little bit more. It takes a little bit of time to get used to. Okay, so let's see. All right, I think I gave you enough for the day, honestly. I can do the next problem, but I will stop here. The reason is that I want you to try the next problem, okay? As a matter of fact, I want you to try the next 2 problems. And I'm gonna do this problem, the next problem, this one, and the next one, which is this one, both of them, and then the third problem, which is this one, all of them in the next class. But I want you to spend some time thinking about the concepts, because I have given you plenty of information for the day. By giving you more is not gonna do much better, because by now your brain is probably has taken sufficient information. So I'll let you process that information, and maybe tonight or tomorrow or even next day, try the remaining problems, these 2-3 problems. Okay, this one is exactly, where is this one? This one is exactly like the last one. I just changed the numbers. Okay, instead of 50, it's 60. I even didn't change the standard deviation. Exactly like the last problem, do it step by step. All right, and go through 8 different steps that I have here in this problem, 6 for this one. Go through these steps and make sure that you can solve the problem, and that way you will get a good understanding of it. Now, this problem, the next one, I did it here. So this is kind of like cigarette problem and nicotine amount. So just try to look at it. And then the next one, this one, is exactly the same problem with the numbers changed. Okay, so that's all for today in terms of lecture, but small announcement, which is we are going to have our second midterm on April 14th, which is Wednesday. The structure of the midterm is exactly the same, the one that you have had. I'll open it at 6 o'clock and we'll close it at midnight. Okay, I'll open it at 6 o'clock and close it at midnight. Any question, anybody, before we go ahead and end the session for today?
No.
Okay. Anybody else? Any other questions?
No question.
Okay. All right. Thank you so very much. You guys have a wonderful day. We'll talk to you on Wednesday.
Thank you. Bye.
Thank you.
Thank you. Have a good day.
Thank you. Bye. You too. Bye-bye.